Welcome to all. Myself, Dr. Santhosh Singh, working as a associate professor in Department of Physics, Institute of Aeronautical Engineering. Today, I am going to discuss about our previous topic. So, we will continue that semiconductor material. So, let's start the topic. So, we already seen in last video lecture some direct band semiconductor and basically the binary semiconductor. Okay, because we already discussed some ternary, quaternary semiconductor. So some direct band semiconductor which are very useful in optoelectronic application was discussed in last video lecture, and that was that direct band semiconductors material, binary direct band gap semiconductor material was gallium arsenide, indium phosphide, indium antimony, gallium aluminum nitride, gallium nitride, and indium nitride. These last three, aluminum nitride, gallium nitride, and indium nitride, you are able to see their lattice constant are something around 3 point something. Like aluminum nitride is have 3.11, gallium nitride have 3.16, indium nitride have 3.54. And apart from above than the aluminum nitride row, all the semiconductor like gallium antimony, indium arsenide, gallium arsenide have some higher lattice constant value. So these lattice constant value also have some particular role. Okay, see, once the lattice constant is high, generally what happen, the band gap value are less. See, like indium phosphide, the lattice constant value are 5.87. So band gap value are 1.35. 6.48 lattice constant value. So indium antimony have a band gap value 0.171. So what I want to say here, generally, if the lattice constant are less, you will get some higher band gap value. I am not telling this is hard and fast rule, but generally it's happened. Why? Lattice constant means, suppose one atom is placed here, one atom is placed here. So distance between these two atoms. Okay. So you know from quantum mechanics, if the particle is trapped inside one box and that box has a length A, means this box is expanded from x is equal to 0 to x is equal to A, and this box have a infinite potential, means your particle will trapped inside this box only. Okay, so let's one quantum mechanical particle have a mass m. Okay, and that particle motion is now restricted only in the region x is equal to 0 to x is equal to A. Okay, so their energy E is something like m square h square upon 2m A square. There are some formula. You can derive this formula. So your energy value is inversely proportional to square of this confinement region. Okay, means if this A value will be small, your E value will be large, and if A value will be large, your E value will be small. So energy band gaps is what? Separation of valence band and conduction band. So let's suppose this is the bottom of conduction band and it categorized by EC. This is the top of valence band and you are mentioning that level by EV. So EC minus EV is EG, energy band gap value. Okay. So these valence band or conduction band are categorized by energy levels. Okay. So let's suppose N is first energy level. If N is value is 1, it will give the value of first energy level. If N is 2, it will give the energy of second level. So once the A value will be very small or small, you will get some higher energy peaks. Okay, and difference between these energy value or energy levels will be also greater, and that difference will only comes in the form of this energy band gap. So generally, once the lattice constant means if one atom is, just now I told, one atom is here and another atom is here. So distance between these two atoms. Now electron is restricted within this point to this point. Okay. So once the lattice constant value means the region of confinement is small, you will get some higher energy level, and so that there are the chances you will get some higher energy band gap value. That's point I want to mention here, and the corresponding refractive index is also mentioned. So once the lattice constant value is small, you will get some smaller refractive index value. What is a refractive index? N is equal to C by V, velocity of light in a vacuum by velocity of light in that particular material. So if you are getting the lower value of refractive index, what does it mean? The velocity of light in that particular material is large. Okay, getting my point? And if V is large, you will get the smaller n. And if V is small, there are the chances you will get some lower value of refractive index. If V is small, you will get some higher value of refractive index. And if V is large, you will get some lower value of refractive index. Means inversely proportional. Okay. So all these things, because all these things are useful for optoelectronic application, and so based on your requirement, you have to choose such material. So we are dealing with semiconducting material for optoelectronic application. So based on requirement, you have to choose what type of material, what type of desired band gap you have to use. Okay. So gallium arsenide, indium phosphide, antimonide, indium antimonide. This indium antimony is known as indium antimonide, aluminum nitride. These are the wide band gap semiconductor. Okay, wide band gap gallium arsenide, indium phosphide, indium antimonide. See their band gap. So gallium arsenide, indium phosphide, antimonide, indium arsenide, aluminum nitride. These are wide band gap semiconductor. Among from them, gallium nitride has a band gap here 3.39 electron volt. Gallium nitride. So no table is available for this. Okay. So I am mentioning some high band gap semiconductors. Well, so these materials are very important. Even gallium nitride is also very important. And nowadays it is used in making a substrate. Substrate is that thing over which you can grow some layer of semiconducting material, or you can grow some layered structure, desired layered structure. Okay. So basically, if you want to grow some layered structure or thin film, there are some requirement. You have to choose some desired substrate. So these gallium nitride can behave like a substrate, and nowadays it is frequently used for substrate. Okay, so this is very important for substrate to get a blue LED laser. See, if you want to develop a blue LED laser, you have to use the gallium nitride substrate. Blue laser, it is the gallium nitride substrate which is used the indium gallium nitride, also indium nitride also. So there are many semiconductors, and these semiconductor have a lattice constant value around 3.1 to 3.5 angstrom. But if you see the other common binary compound like gallium arsenide, indium phosphide, they have 5.6 to 5.8 lattice constant. Okay. So what is the effect of lattice constant over band gap? I already discussed. So that thing I want to mention here. It means if you have some shorter lattice constant value, so there are the chances that you will get some higher band gap value. And once if you are using the material have some higher constant lattice constant, so there are the chance so that you will get a less band gap value material. So actually, what will finally you will get after you will send the material for calculating or for evaluating their band gap. So there are some techniques by that you can calculate or get the band gap value. But these things, suppose you have a lattice parameter value. So based on that, you can speculate. There are the possibility this material will be so the higher band gap or lower band gap. Maybe the result will totally different, but generally you will get a result like that. Now those are direct band gap semiconductor. Now we are dealing with some indirect band gap semiconductor. Direct band gap, and what is indirect band gap? If the I already discussed EK diagram. So once the minimum of conduction band and maximum of conduction band lie at the same K point, that type of band structure is known as direct band gap material. And if the situation is different, let's suppose like that. Here the minimum of conduction band and here maximum of valence band lie at different K points, two separate K points. So such type of situation is known as indirect band gap materials. So here some indirect band gap material are mentioned. See germanium, silicon, aluminium antimonide, aluminium arsenide, gallium phosphide, aluminium phosphide, and silicon carbide. And see there the band gap value. Germanium has a 0.66, silicon has a 1.12, aluminium antimonide have 1.58, aluminum arsenide have 2.16, gallium phosphide has 2.26, aluminum phosphide has 2.45, silicon carbide has 2.42 band gap value. And let's again see their lattice constant value. So lattice constant, germanium has least band gap, but their lattice constant, see 5.65. Silicon has a band gap value 1.12. The lattice constant 5.43. This is has aluminum antimonide have band gap 1.58, but greater than that germanium and silicon. But their lattice constant is 6.14. Now, aluminum arsenide, gallium phosphide, aluminum phosphide, silicon carbide all have the band gap value in the range of 2, and silicon carbide is have a largest band gap value among them, 2.42, and its lattice constant is C, very less, 3.08 comparison to all. So this picture clearly indicate, actually no hard and fast rule, but a clear indication is coming from this discussion. If the lattice constant value is less, your band gap value will be generally high. In previous case also you are seeing, once you are getting the lower lattice constant value like gallium nitride 3.16, the band gap value was 3.39. Obviously indium nitride is giving the exception. That's why I am telling generally, not always, generally. So these are the second list. Here you can find these numbers of indirect band gap semiconducting material and their corresponding band gap value and lattice parameter and refractive indices. And you can find these value in several books or references. Okay, so these indirect band gap material will be very important for UV detector. Okay, UV detector, ultraviolet detector. Nowadays, silicon carbide is very important material for UV detector. Okay. So based on that, what type of requirement you have, you can use your, or you can choose your semiconducting material for optoelectronic application. So you see, when the band gap is very large, the electron volts 2.42, the lattice constant is about 3 angstrom. Just now I discussed if what is the some correlation between the lattice parameter and lattice constant with energy band gap value. So all of them are high refractive index, as you can see. Unlike the normal glass, most of them have a refractive indices 3 and 4. So these are all indirect band gap materials. Some of the common direct band gap and indirect band gap materials are given in the table. Now the choice of semiconductor for any application depend on the band gap. What type of band gap you want, based on that you can choose. Now we have the both type of semiconductor, direct band gap and indirect band gap. How does one choose the required semiconductor? These is determined by the band gap or cutoff wavelength. Why? Because in any optoelectronic application, either photon will or energy will be absorbed in term of photon or photon will be released. So what type of photon will, what the energy of photon that will going to absorb, or what the photon energy will be, which are going to be emission. So the simple answer is the valence band, the conduction band, this is your energy band gap. So suppose this is one particular material X and this material have this energy band gap, and now some absorption of photon will be required for your desired optoelectronic application. So now this material X is going to absorb any photon having energy h nu. So this h nu must be equal to Eg, and then Eg is equal to Sc by lambda. Then from this calculation you can calculate lambda is equal to Sc by Eg. So based on your desired wavelength or based on desired application, you can choose your desired band gap material, okay, for optoelectronic application. Now next case, just now I told either the photon is going to absorb or going to be emitted from optoelectronic application. So now next case here I discussed photon is going to be absorbed. Now next case photon is going to be emitted. So Eg should be equal to h nu. So same way you can calculate the lambda or you can calculate the band gap. So now you know the band gap, you can choose your material. So these things are written here. In optoelectronic, most of the material property which are essential for device functioning is emission or absorption. So this is the due to the band gap which determine what is the wavelength that you can emit or absorb. Okay. So we have EV, top of balance band energy. We have EC also, bottom of conduction band energy, and difference between these two will generally known as EG. So this is the semiconductor which has electrons and vacant states in valence band. Some electrons incident, photon can be absorbed provided E1 minus E2 difference, and that difference will be equal to h nu. If the electron sitting at energy level E1 makes an upward transition to energy level E2, then E2 minus E1 is equal to E1. Just now I discussed here. Based on that discussion, you can choose your desired material. Okay. So all these things already discussed. Okay. So suppose you want to calculate the wavelength value or cutoff wavelength value. Based on that, you can calculate like that with the help of this formula. Means, but what I want to say, if you know the band gap value, or if you know your application, if you know the emitted photon wavelength, so you can choose your desired energy band gap value semiconductor. Okay, suppose you want to do some green light application. So based on green light wavelength, you have to choose your the corresponding energy band gap value material. That's all, nothing more than that. Red light, so choose the corresponding band gap material. Okay. So thank you. So semiconductor material, I already how to choose the particular semiconductor material for optoelectronic application. I discussed. So we will discuss some more thing in our next video lecture. Thank you. Thank you all.
Like, share and subscribe. Hit the bell icon for more updates.